All right, thank you. So thanks everyone for coming to our first seminar of the semester for the Catchment and Wetland Science Seminar Series. And today we're delighted to have Sara Sayedi speaking with us about her PhD work that focuses on combining expert opinions to assess the risk of change in Earth systems. And so my name is Rebecca Free and I will be moderating the event. And I am a PhD student in the CAWS lab supervised by David Olefelt at the University of Alberta. And during my undergrad, I actually was at Brigham Young University in the same lab group. Sara and I overlapped for a little bit. So it's exciting to bring her on and chat about what she's been working on. For some housekeeping, I ask that everyone keep their mics muted for the duration of the meeting, standard Zoom meeting protocol. And if it becomes unmuted, then I will mute you. At the end of the meeting, you can submit your questions via chat, and then I will moderate the questions to direct the discussion. And then last semester, sometimes it worked best for the questioner to unmute and engage in the discussion a bit more once it was their turn. But I do ask that you first submit your questions to the chat, and then that way we can keep things orderly and fair. And then just as a reminder, this seminar is the first of a three-part series. And so later we will also hear from Dolly Kotwala on April 1st, and she will be presenting on organic matter reactivity and persistence. And then on April 9th, we'll hear from Claire Griffin, and she will be presenting on aquatic biogeochemical responses to changing cultural and climatic landscapes in the Arctic. And so if those are of interest to you, then you can head over to our website, caws.ualberta.ca, assuming the same place where you registered for this one, and you can register for those as well. And so with no further ado, I'd like to take a minute to introduce our speaker today. So Sara Sayedi is a PhD candidate in the Abbott Lab at Brigham Young University, and she received a bachelor's degree in environmental science from Isfahan University of Technology in Iran, where she focused on landscape ecology and remote sensing. After that, she attended the University of Tehran for her master's degree, where she researched the application of modeling ecosystem services for decision-making with a focus on water security. For her PhD, she moved to the United States to continue her education in environmental science with a focus on climate change and policy. Her project focuses on different global environmental issues and the risk of changing these systems, mainly because of climate change. The three projects that she's working on are first, vulnerability of subsea permafrost carbon to climate change. Second, societal and ecological danger from abrupt change in global wildfire. And lastly, consequences of changing hydrology on water security. These projects aim to gather the best available expert knowledge to address issues that are specifically important for policymakers. And she also loves to make maps. And as an editorial note, the first time I read this, I thought it said to take naps, which probably is also a fun thing to do. And she's been working at the BYU GIS lab for the past year because she believes maps are one of the best ways to communicate science. And I would also like to add that Sara has an incredible ability to make anyone feel comfortable, and she also has a knack for spreading the gospel of Persian food. And so with that, I'll pass it on to you, Sara.
Okay. Are you guys seeing the right screen?
Yes.
Okay, cool. So hi everyone. Well, thank you for inviting me in that introduction. So as Rebecca said, my name is Sara Sayedi, and today I'm really excited to talk to you about my doctoral research, which is about assessing the risk of change in Earth systems, mainly due to climate change using expert assessment. So what is going to happen in the future is a question we ask ourselves every day of our lives for making different kind of decisions. And we usually try to use the best information we have from the past. And well, if things happen as expected, well, that's great. But sometimes unexpected things like a pandemic might happen that just messes up with all of our calculations. And so because of the uncertainties of future, predicting it is very difficult. Yet it is really important for us for knowing that to making right decisions for our future. Now, due to human activities, one of the things that is changing with an unexpected rate is the Earth. And so many of the assumptions about ecosystems that we have been using in our decision-making process are really no longer valid. And since these unexpected events are not very pleasant and usually have a negative effect on our lives, this Earth system change has raised a lot of attention between both the public and politicians. And more people are now realizing that changes in the Earth system is a really important part of our future. And there is a great need for us to improve our understanding of the change that is happening in Earth. Now, one of the ways that to make informed decisions under uncertainty and limited data is using expert assessment. Now, this is a practice that has been used for very long times, where politicians or other kind of leaders would use the knowledge of people with relative expertise to make the right decisions. For example, in the 19th century, vaccination was a really hot topic, and there was a lot of controversy about how effective it is or should it be mandatory, which the people of power in that time, they used expert assessment to solve their problem. And then in more recent times, in the later 20th century, we see a more more structural assessment that were used by governments in both national and international levels, including for environmental issues such as assessing the ozone depletion, which led to the Montreal Protocol, or assessing the sea level rise from the West Antarctic ice sheet. So in my doctoral research, as Jessica said, I'm using the same approach, expert assessment, where we combine judgments from experts of different disciplines related to one issue to bring diverse types of scientific knowledge into policy-relevant risk assessment. And as you know, the three environmental issues that we are working on are, one, the sensitivity of subsea permafrost carbon to climate change. The next one is the risk of change in global fire regimes on societies and ecosystem, and the last one is the consequences of changing hydrology on water security. So today I want to talk about our recent study with the title of Subsea Permafrost Carbon Stocks and Climate Change Sensitivity Estimated by Expert Assessment. We have started this project at 2018, which our paper was just published a few months ago. And before I start, I would like to thank the BYU Graduate Studies and the Permafrost Carbon Network for supporting this project, and of course all of our co-authors that you see here. That includes all of the experts that also participated in this assessment. So as you know, permafrost is one of the really important components of the carbon cycle, and from the late 20th century, the potential carbon feedback of the permafrost region has raised a lot of attention, where some scientists were concerned that with global warming, the permafrost will thaw and the carbon stocks that have been trapped there for thousands of years can get into the atmosphere. Yet not until recently that we see that permafrost has been seriously discussed in climate change reports. For example, these figures here are from the recent IPCC special report that was published in 2019 that shows projections of change of different aspects of permafrost, such as area change or cumulative carbon change under different climate change scenarios until 2100, which they all pretty much indicate a bigger change under a higher level of emissions. But still, only a small percentage of global climate models include permafrost carbon feedback, and the ones that do, they really cannot capture that its impact adequately. And well, that is for the terrestrial permafrost pretty much. The subsea permafrost, which is found in the continental shelf of the Arctic Ocean, is still really much only acknowledged as an unknown in climate change reports, and it's even barely included in global climate models. Now, we do hear about the subsea permafrost carbon feedback from the media quite often, and there's some mixed messages about how broad or big this carbon emission is going to be. Now, one of the main reasons for this high level of uncertainty is that gathering samples and data from the subsea permafrost is very difficult and challenging, and right now the observations are quite patchy. So we perform an expert assessment to see, based on the best available knowledge that is known so far, what do experts think that might be possible outcomes of the carbon feedback of this region. So first I want to give a little background about the subsea permafrost. And here you see at the last glacial maximum before the marine transgression in the Arctic region, the continental shelf of permafrost, which contained great amounts of organic matter from the undecomposed plant and animal material that accumulated over time, and it's shown here as soil organic matter. And also you can see the methane hydrates. And after that, with deglaciation and global sea level rise, this part of the terrestrial permafrost started to submerge, and consequently, the thermal regime of it changed, and it started to warm and thaw until today. And so now you see there's three major carbon pools here, which was the focus of our study as well. The subsea soil organic matter that I just mentioned, the deposited sediments that refers to the sediments of an organic matter that have been eroded from coastal and terrestrial parts and have been deposited on top of the subsea permafrost during and after sea level rise. And the last stocks refers to the methane stocks that were formed before and after marine transgression that are trapped within and below permafrost in both gas and hydrate forms. Now, because of warming, microbial activities are now using these carbon stocks and generating greenhouse gases. And since we don't know neither the amount of these carbon stocks nor the climate change sensitivity of them, we don't really know how much and at what rate greenhouse gas will be emitted from this region as a result of warming. So as I mentioned at the beginning, we use expert assessment to find our answers. And I just want here to show this diagram from another expert assessment study that I was part of for air quality that was just published recently. And I think it nicely shows the role of expert assessment in science policy communication and how it can play this can play a bridge between the science community and public and politicians by complementing modeling and empirical approaches by including all kinds of factors like those that might not be formalized enough to be included in numerical models. So the specific steps that we took for this study was first we done a comprehensive literature review of both the scientific papers and policy reports to just identify the knowledge gaps. And also at the same time, based on those, we tried to identify a list of experts and also along with a group of lead experts that would help us to design the questionnaire. And so based on those knowledge gaps that we identified, we designed a quantitative questionnaire that after doing several test rounds, we distributed that between the identified experts and then analyzed the results. Now, so in the questionnaire that we designed, we asked about different aspects of subsea permafrost in different timescales. And these include the change of subsea permafrost region extent from LGM until current time, the change of soil organic matter stocks and the added deposited sediments, and then how much these current organic matter stocks and methane stocks could be affected in the future by anthropogenic climate change. And finally, our questions about how much methane and carbon dioxide could be emitted from the subsea permafrost region in 3 time scales from 2050 to 2300 under different RCP scenarios. So this is a format of the question in our survey. In the first part, we asked for the quantitative values, which we wanted to know what values will experts correspond to certain probabilities. And as you can see, for each question, we ask for a 5%, 50%, and 95% quantile. So in other words, the experts thought that there is a 90% chance that the real value for that question is somewhere between the range they provided. And then we eventually use the median of these quantiles to provide a credible range for each question. In the second part, we ask for self-reported expertise and confidence level. And at the last part, we ask them, the experts, to tell us how did they generate that values and what do they think are the largest sources of uncertainty for each question. So we distributed the final questionnaire to about 120 permafrost researchers, and from that we received response from 25 experts from 9 countries, which You can also see here other different characteristics of our experts, such as the primary region of study. Okay, so that brings us to the results, and I want to start with the values for the area and stocks for the current time. So the group of experts in our study estimate 2 million square kilometers for the subsea permafrost extent, which when we compare this to the value that they estimated for the LGM, it indicates around 40% degradation since the LGM. Now, the next category was the amount of soil organic matter that, again, comparing it with what they estimated for LGM, it showed 10% decrease since that time. And in addition to that, there is the deposited sediments that together did show an amount of 560 gigaton carbon in organic matter in the subsea permafrost domain for the current time. And when we express these on aerial basis, it's pretty much the same carbon density that we see at the continuous terrestrial permafrost zone. And finally, the last stocks that we asked for was the methane stocks and the methane hydrates, which, as you can see, it was estimated that it contains a much smaller amount of carbon compared to the soil organic matter stocks. But I also want to point out that these are only the median of the central values, and there was a pretty wide range for some of these estimates, which you can check later in our paper if you're interested. Now, as you know, many different factors such as microbial activity, temperature, sea level rise, and other factors can affect greenhouse gas production. And because of this complexity, before asking about how the greenhouse gas emissions will change, we first asked what percentage of the subsea organic matter and methane stocks could be affected thermally or biogeochemically in the future, regardless of scenario. So here you see at the yellow panel, which is showing the estimated percentage of soil organic matter that can be potentially affected in different years. And in the purple, you see it's for the methane. Now, each dot here is representing one expert and the range they provided. And then each of these black lines are showing, the black lines here are showing the median of each quantile, which, and also the percentages that you see in red, these are referring to the central of the medians. Now, as you can see from the medians, a pretty low percentage of potential effect was estimated for both organic matter and methane, especially until 2100. Now, if we compare these estimates together, it shows that methane may be less sensitive to climate change than organic matter stocks. Experts suggest that this could be due to the depth of some of these hydrate deposits and the effect of different factors such as pressure, temperature, and hydrate composition, which together they make a stable zone for these hydrates. So with that, I will move on to the greenhouse gas emission at the current time. For methane, an annual release of 18 megaton carbon was estimated, and about 25% of that was estimated to get to the atmosphere, which indicates a 75% methane oxidation. And then for carbon dioxide emission was estimated at around 38 megaton carbon in a year, which again, these are only the median of the central values. And for simplicity, I'm not showing the lower and upper values. And so eventually that brings us to our last set of questions, which we wanted to know what percentage of the current gas fluxes will change in the future under different RCP scenarios. Now, similar to the previous panel, again, each dot is representing one expert, and the black lines are showing the median of one of the quantiles, and each color is representing one RCP scenario. So now the first thing that we notice here is that all values are positive, showing that unlike the terrestrial permafrost, where both positive and negative carbon balance is predicted for its future, our experts predicted only positive carbon balance for the subsea permafrost domain. Now, especially for RCP 2.6 and 4.5, this percentage change is relatively low. You see all of the values here are between 0 and 10%. And if you look at the spread, you see there is a pretty good agreement between experts that at least until 2100, there will not be an abrupt change in these emissions. Yet for RCP 8.5, both the amount of change and the level of uncertainty increase, especially for methane fluxes. Now, converting the values we had to carbon dioxide equivalent, which you can see in this panel for the 3 different RCP scenarios, from the current time until 2300. And the green color here refers to the share of methane, and the pink color for carbon dioxide, which, as you can see, methane has a slightly higher share for all scenarios. Now, we see that even though the change of greenhouse gas emissions from this region were suggested to be small and gradual, yet the cumulative greenhouse gas emissions from this area over time seems to be pretty substantial. And again, these are the central values. And if we look at the uncertainty range here, which here it shows, it's shown with gray, we can see pretty much a wide range for all scenarios, especially for RCP 8.5, which it shows that these emissions can be actually much larger than we might think. Now, when we think about the overall role of subsea permafrost in the Arctic carbon feedback and compare the predicted central estimates from our study with other studies related to terrestrial region future carbon feedback, we see for RCP 4.5, where a carbon uptake is predicted for terrestrial part, the emissions from the subsea permafrost region can offset 27 of that uptake by 2100 and 160 by 2300, which suggests that the subsea permafrost can release much more than the terrestrial part can remove from the atmosphere. And then for RCP 8.5, where a net release is predicted for the terrestrial part, for both 2100 and 2300, the subsea permafrost can increase the overall greenhouse gas net flux from the permafrost region by 32% by 2100 and 8% by 2300. So overall, I think the most important points from our study is that, first of all, based on the history of this region and how it has changed during the last thousands of years, in contrast of what we sometimes might hear from media, it was suggested that the climate force of this system is probably going to be pretty slow. Now, yet, especially considering the size of the subsea permafrost, which is 5 times smaller than the terrestrial region, it should be considered as a hotspot. It can have an important role in determining the overall Arctic region carbon balance. Now, the estimates that we have right now are very uncertain. As I mentioned, if you go look at our estimates in the paper, you will see there is a pretty wide range of estimates for most questions. Now, there are different reasons that can cause this uncertainty. Perhaps the most important one of them that was mentioned by almost all of our experts was that, first of all, there is not enough really field observations. And in addition to that, the ignorance of the link between the terrestrial and the subsea permafrost not only increased the uncertainty, but also limits our understanding of some possible thresholds. For example, if the Arctic runoff, sediment balance, and other factors change, will that actually create new conditions that we're not really familiar with? And the last reason is that the lack of synthesis activities between different groups that have access to data in the subsea permafrost community. Now, we know that already carbon is being emitted from this region, yet it is not totally clear whether this is a natural response or if anthropogenic climate change is increasing this release. But for the future, our group did estimate that about 3/4 of the extra emissions from this region can be avoided if we go with RCP 2.6 compared to RCP 8.5. And the last point is that we think all of these reasons indicate that this ecosystem feedback is important even on policy timescales. And there is a great need for increasing our understanding for the feedback of this by both increasing research of this system and a better sharing of the research that has been done so far, so we can improve our overall understanding of the climate system. And also, it's good to point out that this study shows one of the ecosystems that is not included in the climate change projections that we base our targets on. And so actually our current emission targets for the future might be too optimistic and not really good enough. And well, before I finish, I wanted to just give a really short introduction of our current project that we are doing regarding the risk of abrupt change in fire regimes in a global scale. And the idea of this project was started a few years ago during a global Palo Fire working group, and we formally started this project last year with the International Palo Network. And the goal of this project is to document scientific opinions on how fire regimes might change in different regions of the world, mainly due to climate change, and what effects will that change have on ecosystem, climate, and societies. And these are the main sections of the questionnaire that you can see here. And well, so far we had 91 fire experts from different countries and disciplines that have participated in our study, but still we would love to have more experts in our assessment. And so if you are a fire expert and interested, please contact me to join our team. And so finally, I want to end with this slide and come back to our first question, that how can we know what is going to happen? In earth science, we have been depending a lot on models for answering these questions, and considering the complexity of different feedback in the earth, especially the climate driven feedbacks, we know we really cannot capture all the factors and complexity in these models. So it seems really necessary for us to use different approaches and diverse sources of knowledge, like expert knowledge or indigenous knowledge, along with Western knowledge, to find a better answer for all of our questions. Thank you all so much for your time, and I will like to take any questions